Thank you very much, Susan, for the introduction. Mr. President, dear ladies and gentlemen, my name is Julia Boike, and together with my colleagues Uklan Tui and Sarah Chadburn, and actually the entire page 21 here team, I'm presenting Permafrost in the 21st century. And my task will be to first introduce the physical background of permafrost to you, and then second, some of the methods that we employ, and thirdly, talk about the challenges. So in the past, we have seen increasing evidence that something is happening in the Arctic, especially in the permafrost region. So here you see almost like a meteor crater, but it's a mysterious crater, and they have been popping up in the Yamal Peninsula because of drastic changes in these areas. So these evidence of climate change have been increasing in the Arctic, and I will show you some further examples for this. Okay. So what is permafrost? Permafrost is defined by temperature. So the temperature has to be for at least 2 years below 0 degrees Celsius. It underlines about 24% of the northern hemisphere. And if you look at the picture here of the permafrost distribution, you see that the permafrost mostly underlies northern Siberia, in fact. What you don't see here is that we need to drill holes in the permafrost to determine the temperature. So I told you the definition is temperature-based. We don't have satellites that measure the subsurface temperature, as you can do, for example, to other cryospheric elements like snow or glaciers. So we have to have some novel methods to look at temperatures in the subsurface. So what we do is we drill holes in the permafrost, some of them up to hundreds of meters deep. This is an example of permafrost temperatures at 20 meters depth from Alaska on an Alaska transect from south to north. And you see since 1978 the temperatures have been increasing at 20-meter depth in the permafrost. So these are very clear signals that something is happening here and that it's changing very fast. So what are other physical signatures of permafrost? So then there's the ice in the ground. So here you see a picture of Siberia, and you see a large amount of ice, as you see here in the subsurface. And you also see organic material. So the permafrost can extend to about 1,500 meters deep in the ground, and it's potentially very old. And over the time that has accumulated and built up, it also integrated this carbon. So in fact, we have a huge fridge there which stores a lot of carbon, which is currently being frozen, but potentially thawed in the future. So how much carbon is stored in the permafrost? This will be the next picture I show you. If you look at permafrost soils, there's about 1,700 petagrams of carbon, and compared to other soils, you see it's quite some substantial amount, compared also to the atmosphere. It's about twice as much carbon as is in the atmosphere. And again, you see the areas here in the north where it is stored. Now you look at this picture and you think it looks like a smooth surface, but the reality is of course different. So now I'm going to talk a little bit about the challenges and methods that we use to detect changes and how to predict the changes in the future. This is how the permafrost system looks, in fact. So it's not only soil, it's a system composed of the terrestrial component, the coastal component, as well as the submarine component. And it's quite complex. So it is an interface between the processes and the processes happening in the hydrosphere, atmosphere, and in the submarine system. And here you see a picture of the system, how it's covered in the winter with snow. Snow is a very important factor because up to 10 months the surface is covered by snow, so it's a really important factor to consider in the permafrost. So what happens during the summer? The snow is thawed and gives way to a very different system. This is the system in the summer, again very complex. It's determined by the thawing of, for example, the lake ice cover, the cover of the river ice, and of course of the surface. So the active layer is developing in the summer. And again, you see that the system is very complex. There's lots of water bodies, there's lots of rivers flowing, and the system is an intense exchange between the atmosphere. So I told you the page 21 project is about how do we understand these processes all the way to incorporating these important processes in global models. And I'm a field person, so I work on the land installing instruments, and I show you some examples from the page 21 sites and members how we do this. So this is pictures, examples from the field sites. So we put temperature sensors in the ground, we look in the snow, we look also at microclimate, as you can see, eddy covariance as fluxes, carbon fluxes from the atmosphere to the surface and vice versa. We also use kind of novel instruments that look like balloons and zeppelins and drones that you can potentially upscale these data to remote sensing data, validate these data. What you can also see in the background is that there are quite different sites that we have in the page 21 project. So some of the sites are very carbon rich. So you can see here from the Siberian sites here, or very wet, and some of the Canadian or Svalbard sites here, they're very rocky, so very different sites. And this way it makes it quite complex. So, but because we do this big effort in instrumentation and process understanding, we do understand what actually happens at the site and what are the important parameters. So this helps us reduce the uncertainties, and this I will show you in the next slides. So you see here the temperature sensors that we have in the ground to detect the temperature dynamics of the ground, and you see the snow. And the snow is, in fact, one of the determining factors for the ground thermal regime. So look at this picture. You see the temperatures in the ground at, let's say, 3 meters depth in the permafrost. So per definition, so these are measured here, the dotted line. And you see, per definition, they are below 0 degrees, so they are permafrost, and they are continuously increasing, as you have showed. So we try to use our knowledge from the sites to predict the future permafrost temperature state, and we use our site knowledge with snow and etc. and the organic material of the soil and so on, and plug it into our model, and we get a very good fit if we have the site knowledge, as you can see here. So this is the temperatures measured, and this is the best fit that we get when we have the site knowledge. However, if you don't have this knowledge and just take the numbers that are available in the literature, you have a very large uncertainty range. You can see the difference between the light blue color here to the actually measured color is about up to 10 degrees. So you can imagine you're close to 0, you will predict no permafrost where there in fact is still permafrost for a long time. So this is one of the examples of how we try to reduce the uncertainties and incorporate this process knowledge into the models. I will give you a second example of what is important in the permafrost areas, especially for global modeling. So here you see the map of the circumarctic, and you see the permafrost extent in the south. This is the red continuous line here. And you see the dotted line, which is the potential shift in permafrost boundary to the north by the 21st century. What you also see is there's a lot of water in these landscapes, and that is because the permafrost, as I told you, is frozen. There's a lot of water on the top because it cannot infiltrate. So in fact, we have not much water there, but it's all confined to this layer. So what you see here is the global lakes and wetland database map, and you see there's lots of water, and these areas looks like a huge big lake. However, if you do look at a microscopic scale, if you zoom into your sites, this picture kind of looks a little bit different because we are missing a lot of the small water bodies. So up to 50% of the water we don't account for in these large global maps that are used by the modelers. So now I will zoom into one of the sites, just an exemplary site, which is located here, and I will show you how in fact it looks like. So this is the picture when you look through the microscopic lens into these landscapes. So you see these two big lakes. They will be shown on these maps, on the global maps. However, when you look into this map with more detail, you see there's lots and lots of little ponds, and they are really hotspots. The birds love it, the vegetation grows into it. So they are really processes of carbon. And they are very active in terms of they are used by the wildlife and so on. They are hotspots of greenhouse emissions, and they are, of course, warming the environment also because they emit a lot of heat during the winter, for example. So these ponds and lakes are of big importance, and they are not included yet, for example, in these global maps and thus in the modeling. They are also very sensitive indicators of the water balance. The Arctic is really a dry desert, believe it, because it's very little precipitation, especially in the summer. So these ponds depend on the water input during the summer of the precipitation. So if you don't get enough precipitation, they will dry up, and thus the carbon exchange between methane emission and CO2 emission will change. So I've shown you these two examples of how we try to reduce uncertainties within the Page 21 project. But the Page 21 project extends over way more processes and way more sites. Here you see a picture of all the sites that we include in the page 21. So there's 12 sites that range over wide climate and land surface characteristics. And we also align with several other projects, like for example, the Canadian ADAPT project, or the Interact project, the Korean project, and the NG project. So there's various projects that we work together with to have this ongoing goal of reducing uncertainties. And this will now finish my talk. I will lead to the next speaker, who is Hugues Lantouy, and he will talk about the impacts on infrastructure.